All right, listeners, they get this. We're diving into the Banach-Tarski paradox today.
Oh, yeah, this one's a real head scratcher.
So imagine you have a solid ball,
Huh.
like a baseball.
Okay, got it.
You cut it up into pieces.
Uh-huh.
But here's the crazy part. You can rearrange those pieces and end up with two baseballs.
Whoa, wait.
Yeah, each one exactly the same size as the original.
That sounds like some kind of magic trick.
Doesn't it? But it's not a trick. It's a
Yeah.
real mathematical theorem.
A theorem. Seriously.
Yep. Proven back in 1924.
So where do we even begin to unpack this?
Well, I think
Time?
the first thing is to understand that it relies on some pretty out there concepts.
Like what?
Infinity, for one.
Ah, infinity. Always a good time.
And then there's something called the Axiom of Choice.
Okay, that one sounds a little ominous.
And we also need to wrap our heads around the difference between things we can measure in the real world and things that only exist in the abstract world of math.
Got it. So basically, we're about to enter the twilight zone of mathematics.
Pretty much. Let's start with infinity, because that one always gets me.
Right. So try to picture this. You take that baseball and you divide it up.
Okay.
But not just into a bunch of pieces, into infinitely many pieces.
My brain already hurts.
The Banach-Tarski paradox deals with sets that have no defined volume.
No defined volume. How is that even possible?
That's where things get wild. These sets are so complex they can't be measured in any traditional sense.
So we're not talking about like physical pieces you could hold in your hand.
Nope, these are purely abstract mathematical objects.
Ah, okay. So because they don't have a measurable volume, the normal rules about volume don't apply.
Exactly. That's what opens the door to this seeming impossibility, rearranging these pieces in a way that creates more volume.
I'm using air quotes here.
Of course you are.
Than we started with.
It's like we're cheating the system, but mathematically it's completely legit.
Okay, back up for a second. How can something have no defined volume? I mean, isn't volume like a fundamental property of any object?
That's a great question, and it gets right to the heart of why this paradox is so fascinating.
Yeah, I'm hooked already.
In math, we usually use something called the Lebesgue measure to figure out the volume of a set.
Lebesgue measure.
Yeah, it's a way to assign a size to a set, but the pieces created in the Banach-Tarski decomposition are so complex.
Hold on, decomposition. Is that what we're calling this whole cutting the baseball into pieces thing?
Yeah, you can think of it as a really, really weird way of cutting things up. So these pieces are so infinitely intricate that they can't be measured using this Lebesgue measure.
So they're like mathematical ninjas dodging our attempts to measure them.
I like that analogy.
But if we can't even measure them, how do we know they actually exist?
That's where the power of mathematical proof comes in.
Ah, okay.
We don't need to physically build these pieces or even visualize them to know they exist mathematically.
Right.
The proof of the Banach-Tarski paradox relies on a chain of logical deductions based on these accepted mathematical axioms.
So it's like saying, we might not be able to draw a map of this weird island, but we have solid evidence it exists based on, navigation and geography.
Perfect analogy. It's the logic, the reasoning of mathematics that assures us these pieces exist, even if our intuition screams that they can't.
Okay, so the proof is our guide through this uncharted mathematical territory. But here's another thought.
Yeah.
If these sets exist and the proof is solid, does that mean something's wrong with math itself? I mean, two baseballs from one, it just feels like we're breaking some fundamental rule.
I know. It's a natural reaction to feel that way. Our brains are wired to understand the world in terms of finite objects and measurable quantities.
Right.
But the Banach-Tarski paradox throws a wrench in that.
Yeah.
It forces us to face the fact that infinity can behave in ways that totally defy our everyday experience.
So instead of seeing this as some kind of flaw in mathematics, maybe we should see it as an opportunity.
An opportunity for what?
An opportunity to expand our understanding of what math can do, how far it can reach beyond our limited intuition.
Absolutely. It's a reminder that mathematics can lead us to truths that might seem impossible at first, but are nevertheless logically sound and potentially even illuminating.
This is already blowing my mind.
And we haven't even talked about the axiom of choice yet.
Oh, yeah, that's right. From what I've read, it seems like that axiom is key to making this whole paradox work.
It is. The axiom of choice is a real powerhouse in set theory.
Fill me in.
It basically states that given any collection of sets, even infinitely many, you can choose one element from each set.
Sounds simple enough.
It does, but it has some pretty profound consequences, especially when we're dealing with infinite sets.
Okay, so can you give me an example of how this works in practice? Like, how does this choosing thing lead to the doubling effect in the Banach-Tarski paradox?
All right, imagine you have a bag filled with infinitely many pairs of socks.
Infinite socks. Okay, I'm with you.
Each pair has one red sock and one blue sock.
Got it.
The axiom of choice says you can choose one sock from each pair, even though there are infinitely many pairs.
Okay, you're losing me a little. How do you choose from an infinite number of anything?
You can't actually do this physically, of course.
Right, that's what I thought.
But mathematically, you can make this choice.
So it's a purely theoretical choice.
Exactly.
Okay. I think I'm starting to see how this might relate back to the paradox. We have these infinitely many pieces of our baseball.
Mm-hmm.
And the axiom of choice lets us do something similar, like pick out specific elements from each of those pieces.
Precisely. It's this ability to make choices from infinitely many sets that lets us construct the paradoxical decomposition in the Banach-Tarski paradox.
So without the axiom of choice, the whole thing falls apart.
Exactly. It's a crucial ingredient in this mathematical recipe for impossibility.
This is getting deep.
Yeah.
So this axiom is both powerful and potentially dangerous.
How so?
Well, it lets us do these amazing things mathematically,
Right.
but it also opens the door to these bizarre counterintuitive results.
It certainly does. And that's why the Banach-Tarski paradox is so thought-provoking. It forces us to ask some pretty big questions.
About what?
About the nature of infinity, the role of axioms in math, and even the relationship between mathematical truth and physical reality.
Whoa. Okay, I need a minute to process all of this.
Take your time. This is heavy stuff.
But we're just getting started, right?
Oh yeah, we've only scratched the surface.
Listeners' name, buckle up. Because in the next part, we're going to delve even deeper into the paradox.
We'll explore its implications and the fascinating debates it sparked within the world of mathematics.
It's going to be a wild ride.
You bet. Welcome back to our deep dive into the Banach-Tarski paradox. We've laid some groundwork.
Yeah, but now I'm really grappling with these larger questions it raises.
Like what?
Well, we've talked about how it challenges our concept of volume. But if these pieces are so complex that we can't even picture them,
Right.
how can we be certain they even exist at all? It feels like we're dealing with mathematical ghosts.
That's a great point, and it's where the power of mathematical proof really shines.
Yeah.
We don't need to physically construct those pieces or visualize them to show that they exist mathematically.
So how do we know?
The proof of the Banach-Tarski paradox relies on a chain of logical deductions, all stemming from accepted axioms.
So it's like saying, we can't draw a map of this weird island, but we have solid evidence it exists based on navigation and geography.
Exactly. A perfect analogy. It's that logic, that unyielding reasoning of mathematics
Yeah.
that assures us these pieces exist even if we can't picture them.
Okay, but this leads to another question for me.
Shoot.
Doesn't this paradox, with its seemingly impossible outcome, suggest that there might be something off about our mathematical system?
That's a very common reaction, and it makes sense.
Yeah.
Our intuition about volume is pretty deeply ingrained.
Yeah.
But the paradox isn't really a sign of a flaw in mathematics itself.
So what is it then?
It's more a revelation, I think, demonstrating how profoundly differently infinite sets behave compared to the finite sets we encounter in our everyday lives.
So less about a broken system and more about us needing to expand our understanding of mathematics.
Exactly. Pushing beyond that comfort zone of finite, tangible things.
Okay, so speaking of pushing beyond our comfort zone,
Yeah.
we keep coming back to the axiom of choice. It's clearly a powerful tool,
It is.
but one that comes with these mind-bending consequences. Do all mathematicians just accept it? Or are there some who are like, this is too weird, let's find a different path?
That's where things get really interesting. There's actually quite a lively debate within mathematics about the axiom of choice.
Really?
Oh, yeah. While it's widely accepted and used in many areas,
Right.
there are some schools of thought, like constructive mathematics, for instance, that reject it outright or use weaker versions of it.
Interesting. So what's their beef with it?
Well, constructivists argue that mathematical objects should be demonstrably constructible, meaning you should, in principle, be able to build them step by step. The axiom of choice allows for the existence of things that can't be constructed in that explicit way.
Ah, so for those mathematicians, the Banach-Tarski paradox is almost like a cautionary tale.
You could see it that way. A demonstration of what can happen when you venture too far from concrete constructible objects.
It really highlights how different foundational assumptions can lead to wildly different mathematical universes.
Exactly.
Okay, let's shift gears a bit. You mentioned earlier that the paradox is connected to the idea of symmetry.
Yes.
Can you unpack that a little for me? It's still a bit abstract in my mind.
Of course. So symmetries at their core are about transformations that leave something unchanged.
Okay.
Like if you rotate a square by 90 degrees, it still looks like the same square, right?
Right.
These rotations and other transformations form what mathematicians call a group,
Okay.
a structure that describes all the ways you can manipulate an object while keeping its essential properties intact.
So groups are like the language of symmetry.
You could say that.
But how does all this tie back to the Banach-Tarski paradox?
Well, the paradox relies on this surprising fact. The group of rotations of a sphere in 3 dimensions
Hmm.
contains a special kind of subgroup called a free group.
A free group.
Yeah, we touched on this before, but what's important is that free groups have this almost magical ability to generate these paradoxical decompositions. You
Mhm.
can break them down and rearrange them in a way that seems to multiply the original set, like creating something from nothing.
So the fact that this free group exists within the rotations of a sphere,
Right.
that's what makes the doubling effect possible.
Exactly. It's this unexpected link between free groups and these geometric symmetries that makes the paradox so fascinating.
It's amazing how it bridges different areas of mathematics, algebra, geometry, set theory, all coming together in this bizarre, beautiful result. It makes me wonder, are there any practical applications for this paradox, or is it just a theoretical curiosity?
That's a great question, and one that comes up a lot when we talk about these abstract mathematical concepts.
Yeah.
The Banach-Tarski paradox itself doesn't really have direct applications in things like engineering or physics, but the ideas behind it have influenced other areas of mathematics. For example, the concept of amenability, which is closely tied to the paradox, plays a big role in fields like group theory and ergodic theory.
And those have real-world applications.
Oh, yeah, they do. They have applications in areas like computer science and statistical mechanics.
So the paradox is kind of like a lighthouse guiding mathematicians toward new and interesting areas of exploration.
That's a beautiful way to put it. It highlights those unexpected connections between different branches of mathematics, inspiring further research and deepening our understanding of these mathematical structures.
I'm also thinking that beyond any practical applications, the Banach-Tarski paradox has something profound to teach us about the nature of mathematics and its relationship to reality.
I agree. We've explored the mechanics of the paradox.
Right.
But there's a whole other layer here, a philosophical layer. In the final part of our deep dive, I'd love to explore those philosophical implications. What does this paradox tell us about the connection between mathematics and the world we perceive? What broader lessons can we take away from this seemingly impossible result?
Stay tuned for the grand finale. Welcome back to the final part of our deep dive into the Banach-Tarski paradox. It's been a wild ride exploring this mind-bending concept.
It really has. We've gone deep into the mathematical weeds.
For sure, but now I'm kind of eager to zoom out and look at the bigger picture.
Yeah, me too. What are the philosophical implications of this paradox? What does it all mean?
Exactly. It feels like the Banach-Tarski paradox shakes the very foundation of how we understand mathematics and its connection to the world.
I think so too.
So maybe let's start with this. Is mathematics just a tool we use to describe reality, or is it something more, like a realm unto itself with its own rules and truths?
Wow, that's a question that's been debated for centuries. And the Banach-Tarski paradox definitely adds fuel to that fire. It seems to support the idea that math, at least in some ways, goes beyond our experience of the physical world.
Like it's saying there are mathematical truths that have no connection to what we can see and touch.
Exactly. The paradox shows us that mathematically valid results can exist even if they have no counterpart in the observable world.
So it's like math can explore places that physics and our senses can't even reach.
Precisely. It suggests the possibility of a whole mathematical universe out there with its own landscapes and rules.
The universe governed by logic and axioms that don't necessarily reflect the limitations of our physical world.
Right.
But hold on. If math can be so different from our everyday reality, does that mean it's not as valuable or relevant to our understanding of the world?
Not at all. In fact, it's this very freedom from physical constraints that lets math explore new territories and reveal hidden patterns.
Like those non-Euclidean geometries you mentioned before.
Exactly. When they were first developed, they seemed like these abstract curiosities.
Right.
But later, they turned out to be essential for understanding Einstein's theory of general relativity, which completely changed how we think about gravity in the universe.
So even though the Banach-Tarski paradox seems strange and impossible, it could actually be pointing us towards some deeper truths about the universe.
Truths that we haven't even begun to grasp.
It's kind of mind-blowing. It expands our understanding of what's mathematically possible
For sure.
and encourages us to question all those assumptions we have about reality.
Assumptions about things like volume and measurement and even the nature of infinity.
And the axiom of choice, of course. We keep coming back to that. It's obviously a powerful tool,
It is.
but one that gives us these weird results. Is it possible that this axiom, while useful in many ways, might also be leading us astray in some subtle way?
That's a question that mathematicians and philosophers are still debating today. The axiom of choice is undeniably powerful. We can prove so many important things with it.
I get that.
But it also leads to these bizarre outcomes, like the Banach-Tarski Paradox. Some people think those outcomes suggest we need to rethink the axiom's role in our mathematical system.
Or maybe explore different axiomatic systems altogether.
Right. It's like the paradox is making us examine the very foundation of mathematics.
This has been such an incredible deep dive. It feels like we've traveled to another dimension.
I know, it's been amazing. We've encountered infinite sets, non-measurable objects, and paradoxical decompositions. What a journey.
So listeners' name. What's the biggest takeaway you hope our listeners will get from this exploration?
I think the key message is that mathematics is a realm of incredible beauty and also incredible strangeness. It constantly challenges us to stretch our minds and expand our ideas about what's possible.
The Banach-Tarski paradox is the perfect example of that.
It shows us that even when we're confronted with something that seems totally impossible, the search for mathematical truth can lead to amazing and thought-provoking discoveries.
So the next time you're cutting up an apple, remember there's a whole universe of mathematical possibilities hidden inside.
The Banach-Tarski paradox might not give you more apple slices, but it will definitely give you more to think about.
It reminds us that mathematics is a living, breathing field with so many mysteries still waiting to be uncovered.
Mysteries that can push us to question everything we thought we knew about the world around us.